Hello everyone, we are Group A8. Today we are going to present our project on prompt reconstruction. Our goal is to do the reverse of a text-to-image model. We take an image and reconstruct the text prompt that could have generated it. A major part of our project is then systematically evaluating how good our reconstruction is. We chose this topic because we were excited by the challenge of vision language models. It gave us a chance to get hands-on experience fine-tuning these models. And this problem is significant for understanding how VLMs perceive images. For training, we use a Kaggle dataset of 100,000 prompt image pairs generated by Stable Diffusion. As you can see, the dataset is diverse in both style and content. Our pipeline uses several models. Prompt reconstruction. We use and fine-tune the blip model. Text evaluation. We use SentenceBird for semantic similarity and Rog and Blue for lexical similarity. Image text evaluation. We use the clip model to measure alignment. Image evaluation. We fed our new prompt into Stable Diffusion, then compare the new image to the original using hashing algorithms and Hamming distance. Our experiment had two dimensions: the training method, full fine-tuning vs LoRa, and the amount of data, 1200 vs 4800 pairs. We compared these against the pre-trained blip model as our baseline. This diagram shows our overall evaluation process. We start with the original dataset, which gives us a prompt and image pair. Our model then performs reconstruction to generate a new prompt based on the original image. Finally, we take this new prompt and use it for generation, creating a brand new image. To evaluate the quality of this entire pipeline, we made three key comparisons. Between images, we compare the original image with the newly generated image using hashing and Hamming distance. Between image and text, we compare the original image with our reconstructed text prompt using Flip. Between text, and finally, we compare the original text prompt with our reconstructed text prompt using Expert, Rog, and Blue. For image comparison, we use A-hash and P-hash, where a lower Hamming distance is better. For image text alignment, we use the clip score, where higher is better. Our A-hash and Hamming distance results, where a lower score is better, were mixed. The baseline model scored 30.88, while the LoRa model showed a slight improvement at 30.64. Unexpectedly, the fully fine-tuned model performed worse than the baseline, scoring 31.55. This indicates LoRa offered a minor benefit, whereas full fine-tuning had a negative impact on image similarity. The p-hash results presented a similar, more pronounced trend. Compared to the baseline score of 31.39, both the fully fine-tuned 31.52 and LoRa 31.46 models performed slightly worse. The key takeaway from both similarity metrics is that fine-tuning did not consistently improve visual similarity and in most cases had a minor negative impact. This suggests that gains in textual prompt accuracy do not automatically translate to more visually faithful image generation. However, the clip score results were different. The LoRa models showed a clear improvement, scoring over 32 compared to the baseline's 30.52. This means LoRa generated text-related prompts are more semantically aligned with the original images. Next are text similarity results. For all metrics here, Esper's, Roche, and Blue, higher scores are better. The results are very clear. Both full fine-tuning and LoRa dramatically outperform the baseline. This proves our models successfully learn the specific syntax and vocabulary of the training prompts. Our human verification results confirm this. On a 10-point scale, the LoRa model achieved the highest score of 4.84, up from the baseline's 4.40, showing that people also perceive its prompts as higher quality. So what can we learn from all this? First, we realized the quality of our dataset wasn't perfect. We found images that were incomplete and lacked content specified by the prompt, which likely made the training task harder. Second, our model struggled with the reconstruction of highly abstract prompts. This is likely because the pre-trained model wasn't sufficiently trained on such specific or abstract concepts. Third, we noticed a difference between lexical and semantic similarity. Our model learned the syntax and vocabulary very well, leading to massive gain in blue scores. However, the improvement in semantic understanding measured by experts was more modest. This is a key area for future improvement. Finally, we identified a few potential problems. The process was computationally intensive. Fine-tuning on 4800 images took 26 hours. Memory constraints also prevent us from using more advanced models, and the inherent randomness of the image generation C can make image similarity comparisons less reliable. To wrap up, we have three key conclusions for our project. Fine-tuning is significantly effective. Our models powerfully outperform the baseline in all text-related metrics. LoRa demonstrates exceptional performance. LoRa performs as well as or better than full fine-tuning, with far greater efficiency, making it a better overall method. The impact of data volume is complex. Increasing data improves semantic similarity, but not other metrics, possibly due to the model overfitting to patterns in the large dataset. This slide lists the specific models we use. To give you a live look at our best model, we've created a simple demo website. This is an interactive interface where you can upload an image, and our LoRa Blade model will analyze it and generate a text prompt it believes is suitable for creating a similar image. Here are the preloaded images. The first one is a sunflower, which the model predicts very accurately. The second one is a portrait of Henry VIII, and it was also predicted with great precision. Next, let's look at a few test images. I will upload one by one. The first image is our professor, Professor Wang. As you can see, the model predicts him as an Asian person. The second image is one of the pictures from our classroom slides. As you can see, that the model describes it accurately. The third image is the logo of NYCU. Perhaps because this object is more complex and abstract, the prediction results showed a greater discrepancy. This concludes my presentation. Thank you all.